In the previous lecture, we have started the last unit of the course on the topic of algorithms and methods for solving non-linearly constant non-linear optimization problems. In the last lecture, we have described the exterior penalty method for solving constant optimization problems, where basically we have converted a given constant optimization problem into a sequence of unconstant optimization problems, and then by solving this sequence of unconstant optimization problems, we generate a sequence of iterative points which ideally converges to a point that solves the constant optimization problem. So this was the approach in the exterior penalty method. Now in this lecture, we are going to discuss another method to solve a general constraint optimization problem, and this is your sequential quadratic programming approach. This method is possibly one of the popular-most method for solving a general constraint optimization problem. In the sequential quadratic programming approach, what we basically do, we take a quadratic approximation of the objective function and a quadratic or a linear approximation of the constant functions. Then we convert the given constant optimization problem into a sequence of constraint quadratic programming problems. Then by solving this sequence of constraint quadratic programming problems, we generate a sequence of iterative points that ideally converges to a point that solves the given constant optimization problem. So this is the basic approach in solving a general constant optimization problem with the help of the sequential quadratic programming technique. So this lecture is exclusively on this topic, sequential quadratic programming approach to solve a general constant optimization problem. Let's start. Sequential or successive quadratic programming method to solve a constraint optimization problem basically employ Newton's method or quasi-Newton methods to directly solve the KKT conditions for the original problem. And as a result, when we go for employing this Newton method on the KKT system for the original problem, we shall find out that the accompanying subproblem turns out to be the minimization of a quadratic approximation to the Lagrangian function that is to be optimized over a linear approximation to the constraints. Hence, this type of process is also known as a projected Lagrangian or Lagrange-Newton method to solve constraint optimization problems. And by the very nature of this method basically produces both primal and dual solutions. By dual solution, I mean here the Lagrange multipliers associated to the primal solution. To present the basic concept behind this sequential quadratic programming method, at first let me consider some equality constrained nonlinear problem, and subsequently we shall consider some nonlinear programming problem with equality and inequality constraints. So at first let me consider the following problem with equality constraints that considered to minimize a function of n many variables subject to, let's suppose, L many equality constraints, where as usual x has n many components, and we also assume that the objective function and all the constraint functions are twice continuously differentiable. At first, let me go for deriving the sequential quadratic programming approach to solve this equality constraint problem, and the extension for including inequality constraints is motivated by the analysis of equality constraint problem and will be considered subsequently. Let us denote this problem as capital P. Now to solve the problem capital P, we notice that the KKT optimality conditions for the problem P require a primal solution X and Lagrange multiplier vector V such that we have gradient fx plus summation over j equals to 1 to L Vj gradient Hjx is equal to 0 together with primal feasibility conditions that Hjx is equal to 0 for all j is equal to 1 to till L. This is your KKT system for the problem capital P. Now we aim for finding a solution of this KKT system. Let us name it as 1. To find a solution to the problem 1, we notice that this is a system of nonlinear equations, right? And therefore we can employ any of the root finding methods to find a root of a nonlinear system of equations. Here an obvious choice, obviously the Newton-Raphson method, one of the fastest known method to find a root of a system of nonlinear equations. So to find a solution to the problem 1, we aim for employing Newton-Raphson method to find a root of a system of nonlinear equations. Or equivalently, we can also aim for using Newton's method to minimize a function for which this system 1 represents the first order condition that equates gradient to 0. Here I have mentioned that to solve just this system, we can employ the Newton-Raphson root finding method, or else we can formulate an unconstrained minimization problem for which the stationary system is this system 1. In fact, here you may feel that whether I am going to employ the Newton-Raphson root finding method or whether I am going for finding out a minimization problem, an unconstrained minimization problem for which the system 1 is the stationarity system, you may feel they are equivalent, but you know this identification of a minimization problem for which the stationarity system is this one will be beneficial than applying directly the Newton-Raphson method to find a solution to the system 1. We shall find out why this identification of a minimization problem for which the stationary system is this one will be beneficial, that we shall find out. But let us now go for directly employing the Newton-Raphson method to solve the system 1. Towards this, we write this system 1 more compactly, as let's suppose we are going to write here this entire system as wxv is equal to 0, where wxv is a vector valued function whose components are, the first component is this expression. This is your left hand side of the first equation here. Here we notice that this hx we have written in a compact manner or in a vectorial manner. That means the first component of h is your h1, second component is your h2, and the lth component is hl. This is your function h. With this h, we notice that the left hand side of this system 1 is your this expression. Rest of the components of w are given by all these equations. They can be written in a compact manner by just simply hx. So the system 1 is equivalently just this system wxb is equal to 0, where w has this expression. Now to find a solution of this system wxv is equal to 0 by the Newton-Raphson method, iteratively we go for finding the sequence xkvk, where xkvk is given by iteratively by the recursive formula that if we are at the kth iterate, Then to find the next iterative point xk plus 1 vk plus 1, we go for solving wxk vk plus the Jacobian of w at the point xk vk times x minus xk v minus vk is equal to the zero matrix. And a solution to this equation gives us the next iterative point xk plus 1 vk plus 1 is equal to xk vk plus a solution to this equation 2. Now by this recursive formula we can find out this sequence xkvk, and that sequence xkvk is at the end of the day is expected to give us a solution to this equation wxv is equal to 0. Now to find this sequence xkvk, let us go for finding out an explicit form of this equation in terms of the given functions f and the constant functions aj. Now here we notice that this wxkvk by the definition will be just this vector where we will plug the value of x as equal to xk and v as your vk. But what is this Jacobian matrix? We notice that Jacobian of this vector valued function w is given by we can simply find that the Jacobian of W by recalling the Jacobian matrix of a vector valued function which has, let's suppose, p many components f1, f2 till fp. We know its Jacobian is given by the matrix grad f1 x transpose as the first row, grad f2x transpose as your second row, and grad fx transpose as your pth row. This Jacobian matrix is a matrix of order p by n when x is n-dimensional vector. That means if you consider x is in Rn, then for this function capital F, we have Jacobian, a matrix of order p by n. Now recalling this as your Jacobian matrix, we can simply find the Jacobian of this vector valued function w, where w is this expression, the first row as this, then rest of the L many rows are the components of this vector valued function h. We can simply find that Jacobian of w at the point xkvk is given by this matrix, where this grad h is the Jacobian matrix of the vector valued function h at the point xk. Now if we write the Lagrangian function for the given vk is equal to fx plus vk transpose hx, then we notice that this Jacobian matrix of w at the point xkvk can be written as the Hessian of this Lagrangian function Lxvk, or let us denote it simply by Lx, and accordingly we will get here the Hessian of L at the point xk is this first component here, then rest of the elements as those were, let us keep them, and we will find that this is your Jacobian matrix of the function w at the point xk vk, where this L is the function given by Lx is equal to Lx with v is equal to vk. Here I mention that this vk is the vector having L many components vk1, vk2 till vkl, and these components are appearing over here vkj's. Now plugging this expression of Jacobian in this system 2, we find that the system 2 can be written as explicitly this system. Fine. Now this system can further be written as by substituting d is equal to x minus xk as the system this one, right? Because you just explicitly write this term in the expanded form, and you will find that this second term will get cancelled with the second term over here, and finally you will end up with this Hessian times the vector d plus this expression, the Hessian of h at the point xk transpose v is equal to, on the right hand side the leftover part, negative gradient of f at the point xk. Fine. And the second equation here is simply you are just plugging d is equals to x minus xk. Now to find the solution of 2, we can just go for solving this revised system for some value d and v, and let us suppose we denote this dv is your, let's suppose dk vk plus 1, and then the next iterative point xk plus 1 vk plus 1 is given by the previous iterative point xk plus this dk and vk plus 1 as you have found a solution to this equation 4. We have named this system as 4, and here let us denote this Jacobian as the expression 3. With the help of the expression 3, we have found that the system of equations in this system 2 over here can be written as the system 4, and by solving the system 4, the next iterative point xk plus 1 vk plus 1 is identified. And you notice that this identification of the sequence of iterative points xk vk is due to the aim that we are aiming for finding out a solution of this system wxv is equal to 0. To find a solution of this wxv is equal to 0 iteratively, we aim for employing the Newton-Raphson method, and this system is the system of iterative equations. To find a solution of this equation with the sequence xkvk, given the kth iterative point xkvk, we go for solving this equation 2, which effectively is solving the equation over here 4. By solving this equation 4, we are going to find the value d and v, and that is effectively going to give us the next iterative point xk plus 1 vk plus 1. So in this manner we keep computing the iterative points xk vk, and by the Newton-Raphson method we know that if the initial iterative point is very close to a root of wxv is equal to 0, then this sequence xkvk generated by this process is expected to converge to a root of the equation wxv is equal to 0. Now we know that in the Newton-Raphson iterative process, it is not that in the algorithm we just go for keep computing indefinitely, and at the end of the day we expect to get a limit, or we execute the value of the limit xkvk, but rather we terminate the process of execution of these iterative points when we find that there is no improvement of the consecutive iterative points. That means when there is almost no improvement from xk to xk plus 1, that means when your xk plus 1 minus xk is almost equal to the null vector, that means when your dk is almost equals to null vector, then we stop finding these iterative sequential points xk vk, and we declare that possibly this xk vk at which you are finding out xk plus 1 minus xk is almost equal to null vector is possibly a solution to the nonlinear system of equations wxv is equal to 0. And now here we fascinatingly note that when your xk plus 1 minus xk is equal to the null vector, that means when dk is equal to the null vector, then the system 4 reduces to not having this component as well. Here on the left hand side in the second equation, this component is equal to null vector. Now deleting out this and this, we notice that the rest out system 4 is nothing but the system that we have written over here, the KKT system, the system 1 at the point x is equal to xk. So this observation is very fascinating, right? So we can just go for identifying this sequence xk vk by solving the system 4, and you keep computing these iterative points xk vk unless and until you are going to get dk is equal to the null vector, a solution to the system 4, and at the end of the day when your dk is equal to null vector is a solution to the system 4, you effectively have found a solution to the system 1. So this can be employed in a systematic stepwise manner to find a solution to 1 by a sequential procedure. This is just your Newton-Raphson method, and you know effectively this iterative process gives us the sequential quadratic programming approach. In the sequential quadratic programming approach, we do not directly solve the system 4 to find a solution to the system 1, but we go for reformulating bit more this system 4. Before getting into this reformulation, quadratic programming reformulation of the system 4, let me just write out here that after finding xk plus 1 vk plus 1, we go for finding the next iterative point xk plus 2 vk plus 2 by solving the system of equations 4 for the point xk plus 1 vk plus 1. We notice that the system 4 actually is dependent on the previous iterative point xk vk. Given xk, you formulate L, and accordingly now you go for identifying this equation at the point xk. This equation is also dependent on xk. Then go for finding a solution of these unknowns d and v, that is going to give us the next iterative point xk plus 1 vk plus 1. Now you can employ the same process to find the next iterative point xk plus 2 vk plus 2. Now you keep computing these iterative points until you are getting almost no improvement in the consecutive iterates. That is, until ideally you find that xk plus 1 minus xk is equal to null vector. That is, until you find that dk is equal to null vector is a solution to this system 4. Now once d is equal to null vector is a solution to 4, I make a special note here that when d is equal to null vector is a solution to 4, then we see that the point xk at which you have executed the system 4 is a kkt point of the problem capital P. That is, precisely we are saying that 4 is identical to 1 for d is equal to the null vector. And now let us relook the system 4, and looking at the system 4, let us now go for finding out a minimization problem for which the stationarity system is this system 4. But practically we usually don't go for solving the system 4, but rather we go for reformulating the system 4 in terms of a minimization problem. And that means instead of adopting the foregoing process that I have mentioned so far, generating this sequence xkvk and keep computing unless and until you are getting dk is equal to null vector, instead of adopting this process to find any KKT solution to the problem capital P, we can instead employ a quadratic minimization subproblem whose optimality condition duplicate this system 4, but which might tend to derive the process towards a beneficial KKT solution. By beneficial KKT solution, by that I mean that you notice that if I just go for solving the KKT system 1 for the given problem, then you may have some KKT points which might not be effectively a minimizer of the original problem, because KKT condition is just a necessary optimality condition, right? And therefore you may have multiple KKT points. You can have multiple solutions to the system 1, the KKT system of the original problem, and as the system 1 is equivalent to 4, so you may have several solutions to the system 4. Out of these several solutions, we want to actually filter out a KKT point that is effectively solving the original problem capital P. So somehow if we can reformulate this problem 4 in terms of a minimization problem in which the objective function involves the curvature information of the objective function f of the original problem, then it might be expected that out of the KKT solutions, out of the solutions in 4 with d equals to 0, you may filter a beneficial, a better KKT point that is effectively solving the original problem. Now, towards this reformulation of the system 4 in terms of a minimization problem, we notice that we can just go for keeping the second equation over here as it is. Let us keep this second equation as the constraint of the problem, but consider the objective function in the minimization problem for which the gradient plus Lagrange multiplier times the gradient of the constraint is going to give us this equation. we notice that you just considered these two parts, this part and this part, and from here you can quickly figure out what could be an objective function of that minimization problem for which the gradient is this encircled part. For such a function, you notice that we can just go for simply taking off the gradient f at xk transpose d plus half d transpose the Hessian of L at the point xk times d. You go for taking up this as your objective function subject to this constraint, then you notice that the KKT system of that minimization of this quadratic function subject to these equations is going to give us this system 4. And here I just mention that this lxk is the function that I have written over here, this expression. Fine. So you notice that the equation 4 is the KKT system of a quadratic programming problem subject to linear equations that minimize the quadratic function. This quadratic function subject to the constraints as hxk plus these equality constraints. Here you have L many equality constraints. Let us name this problem as the quadratic programming problem at the point xkvk, because you notice that the system 4 is dependent on xkvk and 4 is reformulated by this minimization problem, this quadratic programming problem. And we notice that a solution to this quadratic programming problem is a solution to the system 4. And in sequential quadratic programming technique, to solve the original problem capital P, we iteratively solve this problem qpxkvk. Instead of solving the equation 4 iteratively, we go for solving this qp at the point xkvk and keep generating iterative points this xkvk until we get D equals to null vector as a solution to this problem qpxkvk. As to find this sequence xkvk, we are solving of this quadratic programming problem at each and every iteration. This process of finding this sequence and thereby at the end of the day, after finding dk equals to a null vector and then stopping up the process, this entire process is named as sequential quadratic programming technique to generate this sequence to solve the original problem capital P. We will write this entire process in the sequential quadratic programming problem stepwise to solve the problem capital P after a while. But before that, let me consider two more notes to be written over here. They are very important. That you notice that although these 4 is equivalent to solving this quadratic programming problem at the point xkvk, but notice that inside the objective function of this quadratic programming problem we have the curvature information of the objective function small f of the original problem, because inside L you have your objective function f, right? And therefore inside this term the curvature information of the original objective function small f of the problem capital P is hidden inside of this term. And as this term, the objective function of this quadratic programming problem is taking into account the curvature information of the objective function of the original problem capital P, It is expected that if we go for solving this quadratic programming problem iteratively across the iterations xk vk, we can expectedly move towards that particular KKT point. If there are many KKT points of the original problem, this sequence will move towards that particular KKT point, which is truly a minimizer of the original problem capital P. So due to the fact that this objective function is taking into account the curvature information of the original objective function, solving out this quadratic programming problem at the point xkvk is more beneficial than just go for solving the system 4 to execute the sequence xkvk. So I write it here that the minimization process in 4 drives the sequence xkvk towards a desirable KKT or a better KKT point. And this is due to the fact that the objective function of QP at xkvk includes the curvature information of the function f, and f is the objective function of the problem capital P. But although there is a benefit to solve this QP at the point xkvk instead of solving 4 to find out the sequence xkvk, but there is a crucial drawback to go with solving this QP xkvk instead of solving 4. The crucial disadvantage is that this QP at a given xkvk may be unbounded or infeasible, and thereby this problem QP xkvk will not have a solution even if the equation 4 is going to have a solution. We will have shortly two examples on this unbounded or infeasible QP at a point xkvk. But before that, let us look at a bit more reformulation of this problem QP and try to extend the approach for problems with inequality constraints. To go with further reformulation, let us name this problem as 5, or just go with calling it as simply QP if there is no confusion regarding the point xkvk. We notice that the problem QP can be written as simply an unconstrained minimization problem, where the objective function of this unconstrained optimization problem is lxk plus gradient of L at xk transpose D plus half D transpose the Hessian of L at the point xk times D. This is due to the fact that we look at the constraint. Here, this is your constraint in the problem QP. Now, let us go for writing out this objective function, not simply this one, but let us add with a constant. Let's suppose we are adding up fxk, this constant. And this constant addition is not going to alter the problem QP, right? Now we see that with the help of these equations, we can write this objective function as your this fxk as it is, the first term. Then let us keep the second term also as it is. Then we add vk transpose this expression on the left of these equations. plus let us keep the last term as it is. Now let us go for simplifying this expression, and we notice that this expression is going to give us fxk plus vk transpose hxk plus gradient of f at xk plus gradient of h at xk times the vector v, its transpose, times d plus the last term of d transpose, the Hessian at xk times d. And now look at this expression in the first bracket, this expression in the second term, and the last expression. It says that this entire red expression is the first term is L at xk plus the second term is your gradient of L at xk transpose d plus the last term is as it is. Fine. And we notice that inside this red expression we have already taken into account the all the constraints over here, and therefore the problem qpxkvk can be written as this unconstrained minimization problem where d has l many components. Fine. And therefore you notice that this identification of the sequence xkvk to find a solution to the KKT system of the original problem capital P is effectively solving an unconstrained minimization problem with the help of the Newton's method. Here I have spoken Newton's method because in the throughout the process, in the entire derivation till this point, we have been using the recursive formula of the Newton's method, and therefore this sequence xkvk can be identified with the help of employing the Newton's method on this problem, this unconstrained minimization problem of a quadratic function. And from these reformulation and the observation that the identification of the sequence xkvk is just employment of the Newton's method on an unconstant optimization problem, we can guess about the convergence analysis and the convergence rate of the sequence xkvk to find a solution to the problem capital P. Now here we notice that after this reformulation of the quadratic programming problem at the point xkvk in terms of this unconstrained minimization problem with a quadratic function, this reformulation of 4 crudely supports quadratic convergence of the iterative sequence xkvk, obviously under certain conditions, under some mild conditions that assures convergence of the Newton's method for unconstrained optimization problems. And fascinatingly, we can actually show that out of the several drawbacks of the Newton's method to solve an unconstant optimization problem, only the closeness of the initial iterate alone can establish the convergence of this sequence xkvk to a KKT point of the original problem capital P. So from here we can sense that this sequence xkvk is going to have quadratic convergence rate provided all the conditions of the Newton's method is satisfied, or else you can go for employing one of the quasi-Newton methods, and for quasi-Newton methods there is global convergence properties. And in that case the sequence xkvk can be made globally convergent to a KKT point of the original problem capital P, but with a lesser convergence rate than the Newton's method. Towards this convergence analysis of this sequence xkvk, I would like to refer you A detailed analysis given in the section 10.4 of the Bazar's Research book in its third edition, and especially look at the page number 579, where you will find a convergence analysis of the sequence xk-vk. So, a principal disadvantage of the sequential quadratic programming approach to solve a constant optimization problem is that convergence is guaranteed only when the algorithm is initialized sufficiently close to the desirable solution. Whereas in practice, this condition is usually difficult to realize. It is really difficult to guess an initial point which is sufficiently close to a solution to the original problem, right? And to remedy this situation and ensure global convergence, we can use the exact penalty function that we have been discussing in the last lecture, and accordingly we can find a globally convergent variant of the sequential quadratic programming technique using the absolute penalty function that I was discussing in the last lecture. And here I would like again refer you for this globally convergent variant of the sequential quadratic programming technique to solve a constant optimization problem. Please again refer the section 10.4 of the Bazaris Research book in its third edition. Now I will go for writing a neat stepwise process of the sequential quadratic programming method to solve a constraint optimization problem. The rudimentary sequential quadratic programming technique to solve a constraint optimization problem is as follows. In the method, we aim for finding out a solution of the original problem, capital P. To find a solution to P, we initialize the process with the iteration counter k is equal to 0 and select a suitable initial point. It's not with Lagrange multiplier vectors V naught. Then we start the main steps that solve the quadratic programming problem, obtain dk along with a vector of Lagrange multipliers vk plus 1, and then check whether your dk is the null vector. If dk is the null vector, then we stop the process and provide the point xk-vk as a kkt point of the given problem, capital P. Or else, if dk is not equals to 0, then we consider to update the iterative points to xk plus dk. Then we increase the iteration counter by 1 unit and go to step 1. So this is what your precise steps, that given the initial point x naught v naught, then go for iteratively solving this qp xk vk. Keep solving and keep generating the points by this recursive formula unless and until you are getting dk is equal to null vector is a solution to the problem qpxv. That is what your simple steps in the sequential quadratic programming technique. Now here you notice that I have written down here this algorithm for the problem P, where we just only have equality constraints. For equality constraint problem, you notice that the problem QP is given by this problem minimization of a quadratic function subject to a linearization of the constraints at the point xk, is not it? Similarly, when we have inequality constraints, we will have a straightforward extension that we will have here quadratic programming problem dependent on xk, uk, vk. Vk is associated to the equality constraints. Uk, the Lagrange multipliers, they are associated with the inequality constraints. And here in the constraints, you will have not only linearization of the equality constant problems, but also there will be linearization of the inequality constant problems. And accordingly, if we have inequality constraints in the problem capital P, then here we will have addition of a few linear inequalities together with these linear equalities. Fine. So for equality and inequality constraint problem, the quadratic programming problem QP at the current iterate xk, uk, vk is given by the following problem. A linearization of this inequality constraint at the point xk is given by this gixk plus gradient of gi at the point xk transpose d is less than equal to 0 for equality constraints as those we have identified earlier. This equation for each j 1 2 till l and here for each I 1 2 till m. This is your quadratic programming problem at the iterative point xk together with Lagrange multipliers uk and vk. Uk vector is associated to the vector valued function given by these inequality constraints, and vk is associated to the vector valued function given by these equality constraints. Here I mention that while solving this problem, we should keep in mind that this UK, this sequence UK has to be sequence of non-negative points. That we have to keep in mind, that all the components of UK across the iterations are to be non-negative. This we should keep in mind. But this restriction was not there when we just had these equality constants. Their bk could be anything, that they can be any real number, but as we know, Lagrange multipliers associated to the inequality constants, they are to be non-negative. So we should keep in mind while solving this qp at the given point xk with uk vk, we should find out that solution of this problem duk plus 1 vk plus 1 for which uk plus 1 has all components greater than or equals to 0. This is a special restriction for the problems with inequality constraints. Fine. Earlier you noticed that in solving this QP at XKVK, we were endeavoring to find a solution to this problem as your D and VK plus 1, right? Now here, due to the inclusion of inequality constraints, we should also have UK plus 1 in addition to VK plus 1, where UK plus 1 should have all components non-negative. Now with this QPXK we can just go for employing this algorithm where just this QPXKVK has to be replaced by QPXKUKVK, and all the steps are as they were over here, and that will give us algorithm for the sequential quadratic programming approach to solve a constraint optimization problem with equality and inequality constraints. Fine. Now let me give one example that I have mentioned earlier, that although we have a benefit of solving this minimization problem instead of solving the system 4, but we have a crucial drawback of this solving this minimization problem to find out the iterative points instead of solving the system 4, is that this minimization problem may be unbounded or may have empty feasible region. For such two examples, let me just quickly give you the first example, in which we will realize that this QP can have unbounded objective function. Towards this, you please consider, for example, the objective function to be, say, x1 plus x2, and we need to minimize it subject to, simply let us consider x1 square minus x2 is less than equal to 0. And now taking the initial point as the origin together with initial Lagrange multipliers as the null vector, we see that the QP at the point x0 with u0 is your the problem minimization of the expression of the objective function of QP. You please look at the expression that I have written earlier, and you will find that it is given by minimization of d1 plus d2 subject to minus d2 is less than equal to 0. And you notice that this problem has unbounded objective function, and therefore a question of having a minimum point of this objective function in the constraint will not arise, and hence for this problem we will not be able to find a solution, and hence we will not be able to proceed further. Fine. So we can have this possible drawback that the objective function is unbounded. We can also have the feasible region of this quadratic programming problem inconsistent. For such an example, you just simply consider a constraint, let's suppose x1 square plus x2 square is equal to 1, and you consider any objective function. You just consider this is your one of the constraints, and for this constraint you notice that if I consider the initial point x0 is equal to the origin, then a linearization of this constraint is going to give us gradient of h at the point 0 0 transpose d plus h at 0 0 is equal to 0, which simply gives us the constraint that 1 plus the gradient vector is a null vector, so 0 is equal to 0. This is really inconsistent, right? And therefore we may have possible inconsistency of the constraint set in the quadratic programming problem. So these two drawbacks are there, that unboundedness and inconsistent constraints can be there in the quadratic programming subproblem to execute the sequence of iterative points xk vk. Fine. Otherwise, majorly, if we just forget about these two drawbacks, majorly sequential quadratic programming approach is really a good approach for solving a constraint optimization problem. That it has a globally convergent variant, that is, a sequential quadratic programming approach can be made globally convergent, and the convergence rate of this algorithm is similar to the quasi-Newton methods for unconstrained optimization problems. Fine. Now let me consider one numerical example to execute the sequential quadratic programming approach on a constraint problem where in the constraint set we have both equality and inequality constraints. We are just going to end up the lecture by executing a numerical example with the help of the sequential quadratic programming approach to solve a constraint optimization problem. We consider to solve the problem to minimize 2x1 square plus 2x2 square minus 2x1 x2 minus 4x1 minus 6x2 subject to the constraints that this is your first inequality constraint. The second inequality constraint is given by x1 plus 5x2 minus 5 less than equal to 0. The other inequality constraints are minus x1 less than equal to 0, and the last one is this. Oh, sorry, I mentioned that I am going to consider one problem with equality and inequality constraints. I am having here a problem only with inequality constraints. So let us go with solving this inequality constraint problem by the sequential quadratic programming approach. Here, this is your objective function. Let us denote it by f x1 x2. Now for this problem, you can quickly find out geometrically what is the solution of this problem. You will find that the feasible region is given by the first constraint is upper part of this parabola x2 is equal to 2x1 square intersection with the below part of this line x1 plus 5x2 minus 5 is equal to 0, intersection of these two regions in the first quadrant. So this is your feasible region, this dotted region. Fine. And you can find out the contours or the level curves of the objective function are given by ellipses like this, and you will find that these level curves are going to give us the optimum solution of the problem at this particular point, where this particular point you can find out the x1 coordinate 0.6589, which is actually appropriately minus 1 plus under root of 201 divided by 20, and x2 coordinate is given by 0.8682. Please check it. This point is the intersecting point of this line and this parabola. Fine. So we have a solution to this problem geometrically. We can solve it geometrically because we have here a two variable problem. We can graph out the feasible region and accordingly we can figure out what is an optimum solution to this problem. Let us go for applying the sequential quadratic programming approach to solve this constraint optimization problem. To apply the sequential quadratic programming approach, we at first find the Lagrangian function for the generic variable x with a given Lagrange multipliers u. Notice that by definition, it is the expression if x plus u transpose gx, right? Here u has four many components because u is associated with all these inequality constants. There are four many inequality constants and therefore in this vector u we have four many components. Fine. So here the expression of this capital L you please find out by just considering this expression of f and then plug here u transpose gx as u1 times g1 x1 x2 plus u2 times g2 x1 x2 plus u3 g3 plus u4 g4, and accordingly you please find out what is the expression here. Now to start the process of the sequential quadratic programming approach, we take the initial point as the point 0 1 and also take the initial guess of the Lagrange multipliers as all zeros. Fine. With this x naught u naught, let us go for finding out the next iterative point x1 u1. To find the next iterative point x1 u1, we need to solve the quadratic programming problem at the point x naught u naught. You plug the value of u naught over here in this expression and accordingly you will get the expression of Lx with the given value of u is equal to u naught, and accordingly you will find that this quadratic programming problem at the point x naught u naught is minimization of, you please check this expression, minus 4 minus 6 d1 minus 2 d2 plus 2 d1 square plus 2 d2 square minus d1 d2 subject to 1 minus d2 less than equal to 0, d1 plus 5d2 is less than equal to 0, minus d1 is less than equal to 0, minus d2 is less than equal to 0. Now to solve this quadratic programming problem, the KKT system of QP x naught u naught is given by, you please find out what is the KKT system of this problem and cross check with these equations because you have only the second constraint, this constraint binding at an optimum solution of this problem QP x naught u naught, and you will find a solution of this system as your D is equal to 35 by 31 minus 7 by 31 and U is equal to 0 and the second component as 1.0322. The third component 0, the fourth component is also equal to 0. And accordingly you will find that the next iterative point x1 is given by x naught plus this d that we have found over here, and you will find that the point x1 is given by 1.1290 and 0.7742. Please cross check it. And then I would request you to find the QP, the quadratic programming problem, at the point x1 together with this as your u1 and then go for finding out the next iterative point x2. You will find that x2 is given by 0.6588 and 0.8682, and notice that this point x2 is your this optimum solution, and hence by sequential quadratic programming approach we are able to solve this particular problem. Fine. Now I will end up this lecture by giving a home task, and from that home task we have a very nice conclusion. The home task is as follows: that throughout the lecture we have employed the Newton-Raphson method to solve a system of nonlinear equations, right? And from there we have derived the entire sequential quadratic programming approach. Here I would like to mention that the Newton-Raphson method for root finding, that is actually equivalent of Newton's method for an unconstant optimization problem that we have find out. And the Newton's method for constraint optimization problems with equality constraints is almost identical to the Newton's method for unconstrained optimization problem. Let us see it in terms of the home task. I would like to mention this fact, that so that Newton's method for minimization of fx subject to ax is equal to b, where a is of order m by n, we assume m is less than equal to n, and a is of full rank, that is rank of a is equal to number of rows. For this problem, the Newton's method actually is the Newton-Raphson method to solve the KKT system of this problem. So that this Newton-Raphson method to solve this KKT system of the problem is given by the recursive formula xk plus 1 is equal to xk plus d, and vk plus 1 is equal to vk plus p, where d and p are solutions of this equation. So in comparison with the unconstrained Newton method, the Newton method for unconstrained optimization problem, which follows the iterative sequences as xk plus 1 is equal to xk plus d, where d is a solution of this Hessian times d is equal to the negative gradient. This is the recursive formula in the Newton's method that we all know. We notice that this equation is just similar to this equation with just slightly a bigger matrix. Here we just had this matrix, the Hessian matrix, but here instead of this Hessian matrix we have here this entirely this matrix, right? So just this matrix times, instead of d we have two components d and p, and on the right hand side instead of this negative gradient we have added few more zeros over here, and accordingly we have gotten this system, and which in turn gives us the recursive formula over here. And therefore it is commonly said that the Newton's method for a constraint optimization problem with equality constraints is identical with the Newton's method for unconstrained optimization problems. You please verify this, that why this iterative formula to find a solution of the KKT system of this constraint optimization problem is given by the iterative sequence xkvk that solves this particular system. Fine. With this homework, let me stop the lecture here. Thank you. Thank you all for all of your kind attention.